Okay, so the topic that we are looking at today is called Introduction to GNSS and also receiver structure, okay, and also some basic information. So first of all, let's take a look at the positioning technology these days. So we can divide into three types of approaches. Number one is called aiding and assistance. Second one is called date reckoning, and three is called position fixing. Okay. So for the positioning technology, in general, if we look at how did you say it? There are three areas that one can look at as the trend in positioning. Yeah, and in general, we have this position fixing, meaning that when you want to compute the position, okay, and they can come from various constellation, various technology like GNSS and so on, and to make the positioning more accurate, okay, one can use some aiding or assistance, okay, to help the positioning. For aiding assistance, one of them is called GNSS, which is based on improving the positioning based on the help of cellular system or mobile system, which is called GNSS, okay. But the aiding can be from peer to peer, meaning that from other devices that send some help to your device as well, okay. And then there's this called date reckoning. In this case, we can increase the positioning accuracy for the events where you have some signal blockage. Date reckoning means when you don't get any GNSS signals, so you don't have any position fixing, so you have to get some type of helps, to be able to get positions. And one of them is to use the sensors, like IMU sensors, for examples, okay, that will make you able to estimate some type of positioning. Okay, and so what related to GNSS positioning, at present we talk about three types. Additionally, one is called absolute point positioning, where you get the XYZ of the receiver, okay, based on signals from GNSS only. Okay.
Teacher, excuse me มันไม่ค่อยดังค่ะอาจารย์มันได้ยินเบาๆค่ะ
Can you increase your speaker?
Okay.
Yeah. I think you should increase your speaker. Okay. แล้วเพิ่มเสียงของสปีกเกอร์เราช่วยไหมฮัลโหล
เพิ่มแล้วค่ะอาจารย์
ช่วยไหมครับ
มันก็เบาค่ะถ้าอาจารย์เอาไว้ที่ตรงปากมันจะได้ยินดังอยู่ค่ะ
อ๋อแต่มันต้องถือไงมันก็จะรำคาญเพราะมันต้องถือเอาไว้ตลอดอันนี้ไม่ได้ยินใช่ไหมอย่างนี้ฮัลโหล
อันนี้ได้ยินค่ะ
หรอมันก็ไว้ที่เดิมมันไม่ได้เปลี่ยนนะ I didn't change anything. Can you hear, Pio?
Yes, I can hear you clearly when you pick up the mics.
Oh, I see. So it has to be close to the mouth, but I have to hold it for 2 hours. So,
sorry. Oh.
How about this?
Yes, better? Yes, it's very better.
Is this better?
Yes.
But for this, I don't wear my headphone. Okay. So one is called absolute point positioning, where you get the positions of the receivers, using the GNSS signals only. Okay. And then another type is relative positioning. So in this case, we get the positioning of the receiver XYZ by using GNSS signals together with the correction. Okay, and this is the correction. Okay, normally, it's provided by the base station and then to the receiver. And lastly, this is called a PPP, or some technology similar to PPP. So in this case, you get you still use the GNSS signals, okay, but you get some correction of biases and others to help obtaining the receiver positioning. Okay, so that's how it works. And for GNSS system these days, there are two types of systems. Okay, let me get out from this page a little bit, because I cannot see your face from here when I present. But then I cannot draws. Oh, it's okay. Okay, so for one type is called the global system, and they include like GPS from USA, Galileo from European Union, GLONASS from Russia, and also Beidou from China. Okay. Can you guess which one is the oldest among all these four?
GPS.
Yeah, I think it's GPS, followed by GLONASS from Russia. Okay.
Yes.
Okay. And all this system is called GNSS. Okay. But each system, because it has a lot of satellites, so it takes many years to complete the whole constellation. And at the moment, in some system like GPS and GLONASS, now they are undergoing the modernization or upgrade to newer satellites and new signals. Another system is called regional. So for this type of system, they don't provide the global coverage. They only provide the regional coverage only. Like, for example, from Japanese system, they have a system called QZSS. Okay. Then there's another system from India. The old name is IRNS, but now they changed the name to NAVIC. Okay. So for the QCSS and the NAVIC system, the service is mostly, around the host country only. Okay, and then when we talk about this type of system, there are also some system and satellites. Let's call system or satellites that supports the normal GNSS system to get better accuracies. And one of them is called satellite-based augmentation system. Okay, so in all this system, they are each country launches their own satellites to help broadcast the correction. To broadcast correction. Okay. And in the past, this type of S-bus system, they are used for aircraft, flight positioning across large area and so on. And for example, in US, they have a system called WAAS, or Wide Area Augmentation System. And keep in mind that these satellites, they are the geosynchronous satellite, geostationary satellite. So they're not like a GNSS system. Maybe they are at, normally for geostationary satellite, they are at the altitude of about 35,000 kilometers, okay? And they're used for broadcasting the corrections to aircraft and also to users. And relatively newer system from Europe is called EGNOS, and from China is called SNAS. Okay. Then from India, India has also provided service for some time. The system is called Gagan. And Russia is SDCM. And then for Japan, it's called MSAS. Okay. So normally we talk about these two types of satellite system. One is GNSS satellite constellation, and the other is S-bus satellites. Okay. If you have heard of another system called G-bus, it's also a system that augments or augmentation system, but it's from the ground based, and it's also used for aircraft, but mostly for landing and approach phases. Okay. But for S-bus is used at higher altitudes of the aircrafts, like the en route phases. Okay. However, in some system, like Japanese system like MSAS, and also I think Australia, they also plan some type of service like this, but they give service to consumers as well. However, as you will see later in the lectures, what happens is that S-bus, the accuracy is generally below 1 meter. So it has a difficult time to compete with some other competing technologies like RTK, which is in the 5G standard. 5G and RTK, they work together to the cellular system. So S-bus in a way has a hard time for the competition, but S-bus is maybe more important or more advantages, for the territories or the area with large sparse rural areas and so on. Okay, so for urban environment, maybe RTK with 5G, or RTK by itself, maybe they're more competitive compared to S-bus. Okay, a number of years ago, a company called JPass, they approached our lab as well for some type of testing together to give S-bus service for consumers. And later on, they decided to quit. So I think that they found that S-bus service may not be so competitive compared to other service in the urban environment. Okay, so for GPS is one of the oldest system, and originally, the name was Navstar GPS. GPS represent global positioning system, and it's a satellite navigation system because it's used for navigation of aircraft and for users, for consumers. Well, early on, it was developed by U.S. Department of Defense, or DoD, and it's operated by U.S. Air Force. So it started back in 1978. So it's been quite some time, you know. But it was allowed for free available use by the civilians. Civilians mean just anyone, any citizen, right? In 1983, right? And the system it took from 1978 all the way to 1993, which is 15 years before the whole system is fully operational. Okay, because you know you have like 31 satellites, so it takes some time for launch and you know completing the system. It's a lot of money. Okay, and then sometime early 2000, maybe like toward the end of 2000, you know, the US somehow introduced some errors into the system. So you get like the positioning errors in the range of like 100 meters, you know. Anyway, and so at that time, you know, so about the end of 1900s, 1990s, you know, the US introduced what is called SA, which stands for selective availability. Selective availability, okay, meaning that they introduced extra noise or extra timing error. And I think at that time they added the satellite bias randomly, you know, to the system. So for the users, you get like 100 meters of errors. And you know, if I don't know, maybe you're so young, right? But early 2000, at that time, I think GPS was becoming like popular, but at the same time, it was still not so widespread. Okay, yeah, but then about uh 2005, I think, or I think it's 2000, like in May, the US government, you know, decided to stop the selective availability. So the errors, you know, came down to less than 10 meters. Then, you know, it becomes extremely popular for use. And from early 2000, you know, this mapping and all these the applications, you know, become so widespread, right? Yeah. Then I think from early sometime in 2000, like early 2000, the US government decided to start to modernize the GPS system. So they have to relaunch many satellites. And even today, 2021, not all satellites have been fully replaced yet. Okay. So there are so many applications for GPS and GNSS. They include the military applications and also civil applications in the area of air navigation, land navigation, marine, you know, static positioning and timing, use in space, and also search and rescue, you know, and so on. So there are many applications. So for air navigation, this is a large set of application. So it's used in different phases of aircraft flying. Okay. Another area I think is important is for marine navigation for ships and boats. Okay. And also for survey, you know, the land survey. This is super important as well. Okay. And this is recently from Beito presentation that they talk about different applications for GNSS. So of course, aviation and marine, these are the very big applications. Okay. Then I would like to point out another application in railways. You know that people have been looking at how to give positioning to trains service. Then you know that in consumer devices, you know, in your cell phone or on the wearable devices as well. And for mobility purposes, I think especially in Europe and in China, You get all these bicycles with the positioning service to the bikes, and people can bike anywhere. And okay, then another one that is important is called like drones. Okay, which is used for smart agriculture, or is used for surveillance of various environment, like in construction sites, in agriculture, environmental monitoring for power plants, something like this. So there are a lot of applications involved. Okay, but because there are many systems, so maybe I will focus on GPS. Okay, and when you read from the documents that I shared with you earlier, then you'll read about like Galileo system, for example. But in general, all systems are quite similar in a way that, let's say, for GPS system, it consists of three parts. One is the space segments. Okay, so these are the satellites in space. Okay, these are the satellites, or they call space vehicles, in S band and in L band, that consists of generation 2, 2R, 2F, and also generation 3. Then it consists of the user segments, which are the users that that uses the GPS system in we call positioning, navigation, and timing. Okay, or PNT. Okay, so sometimes you hear the word called national PNT infrastructure, and that's referred to the use of GNSS system for the positioning service, for navigation service, and also for timing services. Yeah. So very importantly, the accurate timing provision in the world is at nowadays is based on GNSS or GPS system. Okay, but they can many network or data network, they obtain this timing as reference to the GPS system, and then they are relayed through the network. Okay. Okay, and the last one is called the control segment. Yeah, this is the control segment. So what are the control segments? The control segments, they have many different control center, like the master control system, master control station, MCS. Then you can have the operational control system, or OCS. Okay, so for the master control station, so I think it's based in Colorado, US, and so this is the ground system, with many antennas, and they operate it together with other scattering stations, monitoring stations around the world. Okay, so what are they for? So number one is, first, this control station, they have to obtain signals from all the satellites, and then analyze all this quality, and then analyze all these errors, analyze all these the orbit information, and analyze some other things, and including like the differential code bias, or DCB. Okay, and this the master control station, they work together with the monitoring station around the world, to derive these errors and these biases, and then they have to send all this information, to all the GPS satellites. Okay, so that the GPS satellites send some of this information to users. Okay, and if you look at the constellation refers to the set of satellites. So for the space segment, the GPS has a satellite constellation. Generally, they have six planes of satellites. Like this is one called one plane. This is another plane. You know, one plane is called like this, and they have like 4 satellites in there. Okay, and the next plane, maybe, you know, they all the next plane of the orbits, you know, they probably like this 1, 2, 3, 4. So this satellite, they, you know, they orbit around the Earth on a different angles, and there are 6 planes, and each plane has 4 satellites. So total you have 24 satellites. Okay. But then, as I mentioned earlier, the total satellites, there are 31 satellites. Can you guess what are the additional satellites for? So for operation, we only need 24 satellites, but in the sky, we actually have 31 satellites. So what do you think the 7 extra satellites for?
For packet?
Say again?
For packet?
For what?
For packet? I mean, for like a spare.
Yeah, like a spare satellite for testing, for expansion or reserve. You know, if some satellites this went out of how do you call it? Went out of service because it's malfunctioned. So these spare satellites, they are used for some type of to replace, you know, that specific satellites. Okay. Okay, the altitudes of the GPS satellites, they are at about 20 kilometers. And as we will know from the next class, is that the altitude is not always constant. It depends on where above the Earth that is flying to, okay? And inclination is 55 degrees from equators. And the period of the satellites is a half sidereal day, meaning that for each orbit, one period, it takes almost half a day. Okay, so in one day you see about 2 times of the satellites. Okay, and these are the different set of satellite from GPS. Okay, these are the oldest, I think. It's called Block 2A, but now not operational anymore. Okay, and I think this probably, let's say, it's not the oldest. Oldest probably block or generation 1. This is generation 2. Okay, so Block 2A launched in 1990 to 1997 now, and they had only 7.5 year lifespan. And at that time, they were equipped with CA code and also PY code. Then Block 2R, now there are 12 operational satellites. So they also consist of CA code on L1, PY code on L1 and L2. Okay, they have onboard clock monitoring, also 7.5 year lifespan, launched in 1997 to 2004. Okay. So some satellite, you know, although you plan it for only 7.5 years, but they last longer. Okay, and then there are Block 2R, Block 2F, and now in new service is Block is called GPS 3, which is the new generation in the modernization generation. Okay, and if I look at some differences between these satellites, for Block 2R, they added the signal called L2C and also included the military M code signals to resist the jamming. Okay, note that for GPS satellites, they give service to consumers like us, but also to military as well. So for the Block 2F, they added the third civil signal, which is L5. Okay, and the lifetime is designed for 12 years and launched since 2010. So there are now about 12 satellites operational. Then for GPS 3, they added the fourth civil signal, which is called L1C. Okay. And let me see what else is here. Begins launching in 2016, and the lifetime is 15 years. So the lifetime is longer. Okay. For L1 frequency is at about 1.5 gigahertz. L2 it's at 1.2 gigahertz, and L5 at 1.17 gigahertz. Okay. So which of these frequency do you think can resist? Okay, let me phrase the question like this. We added L5, which is the newest frequency, which is at lower frequency than L1 and L2. Do you know what could be the advantage, or what could be the important feature of L5 signal? G or PO? Do you know why we added L5, you think? It's at lower frequency. What could be the advantage or the important feature for L5?
To reduce the complexities of receiver antenna.
Say again, I cannot hear you. One moment.
Sorry.
What do you say?
Sorry. To reduce the complexities of antenna design. No.
No, actually no. You know, in practice, for how do you say it? For lower frequency, you can
Yes.
get advantages in terms of penetration. It can penetrate buildings better. It can penetrate the trees better. Okay, so it means that for a lower frequency in general, then you get better reception. That's all.
Sorry.
Okay, and also it gives you another important point is you can totally eliminate ionospheric errors if you have if you have at least two frequencies. Okay, and in most consumers devices, in general you can only receive one frequency, which is L1. But then for L2 is used for military, okay, and or is used for some other purposes, and it costs quite a lot of money. But then L5 is also used for consumer as well. So with L1 and L5, you can have a double difference or iono-free combination. So you can erase ionospheric errors as well. Okay. So L1 plus L5, you can eliminate ionospheric error. Oh, sorry. Iono errors. Okay. Through double frequency. Okay. By using the technique called iono-free combination. Okay. If you don't know what iono-free combination, basically you just subtract pseudo range from one frequency from another frequency. That's all. And then the iono delay term will disappear. Okay. But you may have to multiply with some constant. In later lecture, we will look into details about this. Okay. Okay, so let's take a look. I'm very slow. It's already 5:17. Oh, only 12 slides. But it's okay because generally in another class I will talk very, very fast. But I think when it's online, I have a difficulty to talk fast because I cannot see your face. That's the main reason. Okay. Okay. So for GNSS constellation, so these are different constellation for GLONASS, is Galileo, Beidou, and also GPS. They are global. So they have different planes of satellites all over the world. Okay, and generally they're different planes. See, you can see they're different planes. You know, all systems are like that. Okay. Then when we talk about the Indian constellation like Navik, okay, maybe it's not so clear here. Maybe I can, you know, pull up a little bit. So for Navik or India system, you have only two sets of planes like this. Here we look from, we call it, how do you call it? We call it some type of Skyplot, you know, and you see that it moves like this. Yeah. So they only have 7 or 8 satellite, I think. Yeah, 8 satellite. Oops. And then for Japanese system, they only have 4 or 5 satellites, and this is how the satellites move, you know, above the Earth. It moves at above Japan. This is Japan, okay, and then it also moves down to all the way to Australia, okay. So for us, where we are in Thailand or Myanmar, you know, we can get some service, but it's just not above your head, okay. Okay. Okay, for QCSS, they're designed so that the way they design is quite interesting because they don't have budget to do it all over the world, you know. But they have to give service to Japanese consumers or Japanese islands. So QCSS is designed so that when it passes Japan, it passes with high elevation angles. Because you know Japan, you know, is a country with many, in big cities they have a lot of buildings, right? In the urban area there are a lot of tall buildings. So uh, if the satellites, you know, if there are only few satellites and they travel above the sky with very low or relatively lower elevation angles, the users cannot receive the signals that well, okay. So in Japan, QZSS is designed so that when it, you know, pass overhead of big cities, it passes with high elevation angles, so users can receive the signal well. Okay, so different system they have a different things. Next, here are some system parameters. I'm not, maybe I don't need to go in so super detail on these, but I helped collect this information for the Thai Space Agency about 2 years ago. Okay, so let me pick some of these and then see which one is important. Okay, so okay, so in each system you have a different number of satellites. Okay, I think for GPS they vary from 30, 31, 32, something like that. You know, it's not fixed. And then for Peito, which is the Chinese system here, it's quite interesting because they have various orbit. In particular, they have 5 geostationary satellite at 35,000 kilometers. Okay, I'm not so sure what they are for, but I think they are for some type of SMS service. But maybe the S-bus is included in here, I think. Yeah, as we have the Peito training during these 2 weeks, I think I'm gonna ask them about this. And then QZSS and then ARNSS or Navik, which is the new name. Okay, and for the accuracy, okay, each system, you know, they normally publish the accuracy, average accuracy all over the world, like the horizontal accuracy and also the vertical accuracy. Okay, and you know, in some region maybe you get better errors, some region you get worse errors, and I think they publish like every year. So these numbers sometimes change even, but in general, it is found that the longer the longer the satellites have been launched and operational, the errors tend to decrease. When you have newer satellites in the system, it contributes to larger errors. So don't worry too much about these errors because they increase, they decrease, and all that as well. But in general, for regional satellites like QZSS and IRNSS, they seem to have larger errors. Okay. And then, okay, and then for each system, they have their own reference frame in terms of the positioning. You have to, what happens is, for positioning, everywhere in the world on Earth, there are some errors. The Earth is not fully circle. There are some height, they call geoids, some height above and below the sea levels. So in each system, they also devise some sort of like correction, positioning, how do you call it? Maybe it's called geographical reference frame, okay, for each system. Yeah. And if you get XYZ from the GNSS system, that is the positionings from certain coordinate system, but it's not the exact XYZ on your surface. Okay, so this correction have to be made, and the correction depending on the surface is based on this reference frame. Okay, and then for the timing purpose, because GNSS system also provide the timing accuracy, the timing service, each system also comes up with their own reference timing standard as well. And a lot of them are quite related to anyway. Okay, so when you read the paper that I sent earlier, they have like some comparison on the timing as well. Okay, this page is related to what I mentioned earlier about the operational station. So for the GPS ground segment, for example, okay, so they have the master control station in Colorado and also alternate master control station at the Air Force Base. Where is it in here? Let's take a look. So it's the orange, right? Which is the master control station. One is here. And the other one, I don't know where it is. Here. It's probably here. Yeah. Air Force Base, Vandenberg. So I guess this is on the west coast of US. And the main station is Colorado. This is an alternate. Just in case if the master control station, malfunction, I guess. No. Because they have to give 24/7 service, right? And then there are 12 monitor stations all over the world. So you can see this, the circle with the red colors is all over the world. It's in United Kingdom, of course, it's in Washington, D.C., is in Alaska, is in South America, is in, where is this? Maybe Korea? I don't know. It looks like Korea, right? I guess, yeah, I think it's Korea, It's like all over the world. You have to put this monitor station for some type of monitor. You have to monitor the performance all over the world and send all this information to the master control station for processing and all that. Okay. And then I think they also have some other ground antenna that installed all over the place. And this is the purple, right? The color looks a bit difficult. So these are not station. These are more like just antenna by itself. Any questions so far? Okay. So today, maybe we have some time. You look at Skyplot. Pio and G, have you seen Skyplot before?
No.
No. No.
So when you play with the GNSS receiver, you didn't see Skyplot at all?
I see the one Skyplot.
Say again? Yes.
I see the blog. I didn't think it's Skyplot.
Oh, I see. It's called Skyplot. Yes.
Yes.
So Skyplot is like when you look up to the sky and it shows which satellite are visible above your location. Okay. So depending on where you are in the world, when you look up the sky, you see different set of satellites, right? Because there are satellites all over the globe. And here is these are specific to GNSS satellite. Okay. So the sky plot is plotted with the circles. So the outermost circle, depending on the software, but the outermost circle represent low elevation angle. Okay. And then the innermost here, this is like a 90 degrees elevation angle, which is meaning that you just look up the sky just above your head, right, at 90 degrees. And then this is like 0 degrees. Okay. And depending on the software, different software may have different circles for references. In this case, if we have only three circles, so each circle represents a range of how many degrees? G?
3 degree.
Yeah, exactly. Yeah, because here we only have 3 circles. So for each one is from 0 to 30 degrees, and then 30, let's say 31 to 45. Oh no, sorry, to 60, and then maybe 61 to 90 degrees, right? Okay. Additionally, so you see that any satellites that are near the outer circle, like these, like these 7, 12, 18, 22, these are at the low elevation angles. And some satellites like 14, 193, they are at relatively higher elevation angles. Additionally, in this plot, we also look at direction, compare with the north direction. Okay, so this is the 0 degrees. And then we can measure from the north on what degrees we are looking at. So in this case, we have 360 degrees. Okay, we call these angles as the azimuth. Okay, so if you look at the further away from the north direction, the more angles of the azimuth you have. Okay, so if you are at the satellite number 18, this is at 90 degrees from the north, which is on the east direction. Okay, and if you go over more angles, like number 1, you at the south side, the azimuth is about 180 degrees, and so on. Okay, so you get what it means, right? And also, depending on software, the colors typically may represent each system. Okay, so in here, how many Peito satellites do we see? Peito is BDS pure
7.
7, right? Which is exactly, yes. And also in this software, depending on the software, right? In this software, some satellite like this have gray colors. Can you guess what happens? Why do they have gray colors?
Unavailable.
Yeah, sort of like a very low SNR. So in a way, unavailable or almost unavailable, right? So you cannot receive the signal well. Okay, next. The format. So as you see earlier, when you get the positioning, in most receivers, how do we get the positioning? Okay, there's a format called NMEA by the National Marine Electronics Association. Okay, this is one format. So in this format, if you connect your simple GPS receiver or GPS module and antenna, then when you connect to computers or your device, it will give out this information at each time. Okay, and there are different information they give out. For example, they give out the positioning. I think that here are they call ID, okay, plus the 3 letters, which represent what type of information that are received. So if it's GGA, normally this is when you get the positioning, okay. And then for GSA is when you get the which satellite number, I think, that you see. And what else? I see. Also at the front, they have like GP. GP is like GPS. I think GL represent Galileo, for example. And there are other like information as well. Okay, I think next page there are some summaries of this code. Like this. So if you see like a GP, it means GPS or S-bus satellite. GL is for GLONASS. Sorry, earlier I said Galileo. And then GA is Galileo, BD, Beidou, QZ, QCSS, and etc. So these are the talker ID. Okay. And then there are locations. For example, if it's GP and then followed by GGA, then first you start from the time, which is UTC, right? In Thailand, what is the time compared with UTC? Do you remember? Plus what?
+7.
+7. Yeah. So how about in Myanmar?
630 +630.
Yeah, 6.5, right?
Yeah,
Exactly.
6.5.
So here, the first term, this is the first set of numbers. These are the time, hour, minutes, and then second. Okay, followed by the latitude of the position. So in NMEA, they give out the latitude and longitude of your position. Okay, and then followed by this is also longitude, right? And then followed by the mode of the positioning, like is it valid or invalid? Is it GPS, DGPS, RTK, and etc. Okay. They also give the quality, the number of track satellite. In this case, there are 8 satellites that are seen for GPS, because this is GPS. Okay. And then they give you the horizontal dilution, which is the quality. Then they give you the altitude as well. Okay, and then also the height of geoid, which is the height of this surface compared with the ideal or idealistic surface above the WGS ellipsoid. Okay, so the ideal reference is based on like the Earth is an ellipse. Okay, but in real life the land is not like ellipse, right? Because it's up and down depending on where you are in the world. Okay, and then at the end there are checksums or like CRC, I think. Okay, and also in some applications they give the ID of the satellite constellation depending on what system you're looking at. Say, for example, GPS, the number of ID is 1 to 32. Then for GLONASS, it's number 65 to 88. So you can tell that GPS comes before GLONASS, right? And then for QCSS is 193 to 195. For Peito is 201 to 235. Okay. But then in some software, maybe they call from 1, even Peito, they call from 1 to 30, something like that. But they use different colors. So that depends. But this is for the NMEA standard. And these are the ID for each, the satellite for each system. And then for Galileo is 300 plus. So you can tell that the later system that I guess apply for this ID, they are Galileo, right? Okay. And another one for NMEA, this is GSV. This is the satellite in view, meaning that which satellites are visible. So whichever command line start with GP, GSV, it represents the satellite, visible satellite for GPS. Okay. And then the next number is number of sentences. I guess this is like how many lines are there. Okay. Because it can be long. And which line number are we looking at? Okay. And then followed by how many satellites. So this is similar to previous page that we looked at. And then it will go on for each satellite, like satellite number 1, we call PRN1 at elevation 40, azimuth 83 degrees, and what are the SNR levels, right? Generally, the SNR level above 35, 40, they are considered good quality. And then in this case, the next one is PRN2, which is the satellite number 2. And so there, like elevation, azimuth, and so on. Then followed by satellite number 12, 14, and so on. And then if there are more lines, you go to next line and then read out, okay, and so on. Okay, so this is NMEA. But the GNSS receiver that we use in the lab, I guess you can get NMEA standard information. But for us, we look into raw data, so it's a bit. How do you say it? Is you get more information out of it, right? Okay. And the next one is GSA, which is the satellite status, and this is like the delusion of precision or DOP. Okay. So DOP is like the quality of the positioning that you get. The larger DOP, I think, larger DOP generally means better. Yeah, like better quality. Okay. If you get lower DOP, then you have lower quality. Then because it's about positioning, so we have a horizontal DOP or HDOP. Then we have vertical DOP or quality of vertical error. Okay, and then all together we call PDOP. It's like a total quality of the position in 3-dimensional. Total 3D positioning quality. Okay. And yeah, the rest you can just read, they're just each PRN involved. And then what are the DOP? The DOP comes in 3 numbers. Start from PDOP, HDOP, and then VDOP. Okay. And for each satellite, you don't get the same thing. We can, okay. Oh, also we don't get the HDOP, VDOP, and PDOP from each satellite. We get this quality information from all satellite because we use all satellites to compute the positioning. Okay. So besides this, the message type earlier, like GSV or GSA and all these, there's also some other information as well that in NMEA you can get information. Okay. Okay, and so what's the difference between azimuth and also elevation? We saw already that these 2 parameters, they are important parameters to specify where the satellite is, right? Okay. Yeah, I guess this is just just another way to look at it. So elevation angle, here you look at how the satellite, what's the angle compare with the ground or compare with the horizontal line. Okay. For azimuth you measure from the north. What's the angle from the north direction? Okay. And then opposite to elevation angle, you can also get this called zenith. Okay. So elevation and zenith, when you add it together, you get 90 degrees, depending on how you look at. Okay. So these are different names. Okay. And then for GPS signals, as mentioned earlier, we have L1, we have L2, we have L5. We also have L2 in general as well for PY codes. Okay, but these are for military. But the new GPS signals, depending on which satellite you look at, now we have 3 frequencies that we look at. Okay, and for each frequencies, you have different signals in there. Right, you have CA code, you have L1C, you have PY codes, you have L2C, M code. I guess M code for military, and then you have L5I, L5Q. Okay, there are different modulation, in there as well. And for here, these are just the accompanying modulation scheme for each type. Okay, and in BPSK, they just binary modulation scheme for bandpass system, for like wireless system, very low speed. Okay, then later on now they have like they call it binary offset cosine, I think, BOC. So these are they have better spectrum shape compared to the typical BPSK and MBOC as well. So these are the new type of modulation scheme with better bandwidth. The second lobes, they have lower spectrum, for example. And for GPS signals, they generally send information to us. It's called navigation data. Very low speed, only 50 bit per second. Okay. So you see that some signals, they don't give out any navigation data. They use for some other purposes. Okay. If I remember right, like L1, some L1C, sometimes they use for like some type of like some L1C signals, they don't give any navigation data because they just use for some type of quality testing, and so on. Okay. Anyway, so let's go on. So as you see now that we go very deep, so compared to the training that we had today, I think it's a very different scale of depth. Okay. So we're not going to go too deep in here, but let's go in a little bit just for fun. So we have L2C. L2C is the L2 for consumers, not used only for military. And we can use 2 frequency like L1CA and L2C for iono correction. Okay. For example, and they often say that for L1C, the power is higher compared to the traditional L1CA signal. So you can receive it under trees or even indoors. Okay, so that's some benefits. Also, they say that L1C gives you faster signal acquisition, which means you can synchronize with the signal faster. Okay. L5 is also very important. L5, the shape is like this, different from L2C, and it's suitable for aircraft. And if you use L1CA plus L5, you can get iono correction because you can only do you need only 2 frequencies, right, to get iono correction. And then if you can use together with 3 frequencies like L1, L2C, and L5 signals, then we can get the accuracy below 1 meters.
accuracy, errors below 1 meter. Okay. And then L1C, L1C is like a newer type of signals for L1 frequencies, but still the same frequency as L1, the traditional L1. The traditional L1 is called L1CA. Okay. And let me see what else. Yeah, that's all. It's the modulated with the binary offset carrier. Okay. Also, this I think L1C is included in the new satellite because it operates in, they call interoperability between GPS and other system. And I guess meaning that the other system can also receive L1C as well. Okay. That's all. I don't know what this is for. It just says it has no error correction codes. By the way, this information I get it from the GPS website. Okay. Because earlier I was also quite curious about each type of signal. What are they for? Okay, so here let's just have a quick comparison before we go on a break. What time is it? As I mentioned, I'm so slow now when I speak online. Okay, so okay. So earlier we talked about GPS, okay, and there are three frequencies at L1, L2, and L5 that we transmit. L1 is around here, 1.7 gigahertz. L2 is about 1.2 gigahertz. And then L5 is at lower frequency at L5 at 1.1 gigahertz. Okay. Then for Galileo or GLONASS is the Russian system. They also have frequency called G1, G2, and L3. Okay. They're not at the same frequencies, but they are near these frequencies. And then for Galileo, they transmit with 3 bands called E1, E5, and E6. For Peto system, you have I don't know, I think it's called B1, B2, and B3. Okay, so it gets a bit confusing where they mark or where they label 2 or 3. You know, so I always use these pictures for some type of references. Okay, and then for Japanese they have 4 bands: L1, L6, L2C, L5. Okay. Then for the India they have I think L5. Okay. And maybe I think then S-bars satellite. S-bars they also have L5 and as well. Okay. L5 and S-band. Okay. And on this side, this is just the type of frequencies for each constellation that we look at. Okay, this is a very good file as well. If you have a chance, try to download this technology report called GNSS Technology Report. I think they have 2 reports. One is on the technology, which is more detailed than the file that I sent to you earlier. And they have an alternative report. I think it's called application report. Okay, and very, very good information, a good source, to read. Okay, so I have a question before we take a break. So what information does each satellite send to a receiver, you think? G and Pure. So think about it for a few minutes. I'll come and ask you. Okay. Okay. If you have an idea now, you can answer now. Otherwise, maybe we take a break and we come back and you answer to me. Okay. Okay. You want to answer later?
Yes.
Okay. Okay. So let's have a 10-minute break and we come back. Okay. maybe I stop the recording now and then I record again later. Okay.